Hello, my dear students. Welcome to my new lecture. In today's class, we are going to discuss about radioactive decay laws, a statistical analysis. That means we are going to find out the number of nucleus that is going to be decayed in a given time t, or the number of nucleus that is remaining active after time t. Okay. Now the first thing is decay processes are random and probabilistic. Okay, so the decay that is occurring is random. Here one simply knows that in a radioactive element, radioactivity is taking place, or it is definite that a certain number of atoms will decay in a given interval of time. But one never knows which particular radioactive nuclei will decay. So you know that suppose you have 10 crore nucleus, then after some time it will become 9 crore nucleus. But which of this 1 crore will decay, we do not know. Okay, we cannot know which nucleus will decay at a given time. We can only calculate the number of nucleus that has decayed, but which one has decayed we cannot say. Okay, it's just a matter of chance, or you can say it is probabilistic. Okay, and it is explained by quantum mechanics. How this is happening is not in our syllabus, but the number, how much is getting decayed, is in our syllabus, and we'll be restricting ourselves to that only. So this process is spontaneous. You know, we have already studied the radioactive decay process is spontaneous. It cannot be started, it cannot be stopped, and it cannot be accelerated or retarded by any physical change like temperature, pressure, force, or any chemical change. So you cannot retard, stop, accelerate, or start any radioactive process. It is spontaneous, it occurs naturally. Okay, you cannot change it. Now in this phenomena, the parent-daughter chain continues. Original radioactive elements are called parent nucleus, but new element is called the daughter element or the disintegrated nucleus. So the new element are called disintegrated nucleus or daughter nucleus or decayed nucleus. Okay, for example, here uranium is converting to thorium by releasing an alpha particle. Then this is the parent nucleus, this is a daughter nucleus. Here the thorium nucleus is converting into protactinium, releasing a beta minus particle and an anti-neutrino. So here you can see that the mass number remains same and the charge number increase. When the mass number remains same and the charge number increase, in that case that will be a beta minus decay. Here you can see that the charge number decreased by 2 and the mass number decreased by 4. That means this is an alpha decay. Okay. Now in this phenomena, alpha and beta particles and gamma rays are emitted. Okay, you know that in a radioactive phenomena, alpha particles, beta particles and gamma rays are emitted. We have already discussed this in the last class. For a given nuclei, at a particular time, emission of either alpha or beta particle takes place, but never both at a time. This is very important. Now, if the nucleus is decaying according to alpha decay, then it will not show beta decay at that time. So both alpha and beta decay cannot occur simultaneously, right? Then due to the emission of alpha, beta and gamma during radioactive decay, the mass of the parent nuclei goes on decreasing. Obviously, the parent nuclei is continuously decaying, right? So its mass continuously decreases. The mass of the parent nuclei decreases and the mass of the daughter nucleus increases. Okay? Deflection of radioactive radiations was measured by Rutherford in electric field and it is shown below. Now, alpha particles are positively charged, right? So suppose it is deflecting in this direction, then the beta minus particles will deflect in this direction. This is the negative plate, so alpha particle will attract towards the negative plate and the beta minus will be attracting towards the positive plate. But the gamma rays being chargeless, they are not deviated by the electric or magnetic field, right? In the same way, the deviation in a magnetic field, you will see that the gamma particles are not deviated in a magnetic field. Alpha particles and beta particles deviate in opposite directions. Okay, so if this circle is formed in this direction, this circle will be formed in this direction. Okay, for alpha and for beta. Now, again coming to the decay law or the statistical analysis. So according to Rutherford and Soddy law for radioactive decay, At any instant, the rate of decay of radioactive atom is proportional to the number of atoms present at that instant. So that means the rate of decay, dn by dt. The rate of decay is dn by dt, or you can write a minus here because it is decaying with time. That means n is decreasing with time. So to keep it positive, add a minus here. Okay. So the rate of decay, that is minus dn by dt, is directly proportional to the number of active nucleus. That means what? This is very important. That means as the number of nucleus keeps on decreasing, so as the number of nucleus decreases, the rate of decay also decreases. This is very important. As the number of nucleus decreases, the rate of decay also decreases. So suppose initially there were 10 crore nucleus and it was decaying at a particular rate x. Now you have only 1 crore nucleus. In that case, the rate of decay will be less than x. Understood? So as the nucleus keeps on decreasing, the rate of decay keeps on decreasing. So the rate of decay is directly proportional to the number of active nucleus. So the proportionality constant is called lambda, and this is also called the decay constant. So this lambda is the decay constant. So you'll get minus dn by dt is equal to lambda n. Now just take n here and take dt there. You will get n by n naught is equal to e power minus lambda t, or n is equal to n naught e power minus lambda t. So this is the formula for number of active nucleus at any given time. So this is the formula for number of active nucleus at any given time. Okay. So at t equal to 0 here, while integrating, we assume that at t equal to 0, the number of nucleus is n naught, and at any time t, the number of nucleus is n. Okay. At t equal to infinity, we will see from here that n becomes 0. That means all the nucleus has decayed at t equal to infinity. So therefore, for a complete decay of a radioactive nuclei, it takes infinite time. So a radioactive nuclei will decay completely after an infinite time. Okay. So now, what is the number of nucleus that has decayed after time t? Okay, so the total number of nucleus is conserved. So that means if this is the number of nucleus left at time t and this was the initial number of nucleus, then the number of nucleus that has decayed is equal to n dash, and that is n naught minus n, because initial number of nucleus was n naught. Now the number of nucleus is n. So the number of nucleus that has decayed is n naught minus n. And n is what? N is n naught e power minus lambda t. So if you take n naught common, you will get n dash is equal to n naught into 1 minus e power minus lambda t. Okay. Now what is this decay constant? Listen carefully. Decay constant, first of all, is independent of all the external factors like pressure, temperature, and any other force or the chemical conditions. The decay constant depends only on the type of nucleus. So if the nucleus is fixed, the decay constant is fixed. Okay. So decay constant can also be defined as lambda is equal to, so you know that dn by dt is equal to minus lambda n, right? So dn by dt divided by n is equal to lambda, with a minus sign. So the lambda, or the decay constant, is equal to minus dn by n divided by n. That is the rate of decay at any given instant divided by the number of active nuclei at that instant is the decay constant. Okay. This can also be written as minus dn by n divided by dt. Just take this here and dt. Okay, this can also be written as minus dn by n whole divided by dt. Okay, so this is equal to the probability of decay in unit time. So the probability of decay in unit time is also defined as the decay constant. So decay constant can be defined in two ways. First is the rate of decay per number of active nuclei. Okay, and the second is the probability of decay in unit time. All right. Till now, we have discussed that the number of active nucleus left after time t is n naught e power minus lambda t. Okay. Now we will generalize this, and suppose we know the number of active nucleus at any time t1 or t initial, and the number of active nucleus n final at any time t final. Then you will integrate this. Dn by dt is equal to minus lambda n, right? So you will say dn by n is equal to minus lambda dt, and this time we will integrate it from not t equal to 0 but t equal to t initial to t equal to t final, n equal to n initial to n is equal to n final. So from this we will get n final is equal to n initial e power minus lambda t final minus t initial. So from this relation we can calculate the number of nucleus finally if we know the number of nucleus initially and we know the time interval. Okay. Now the next important definition is half-life. What is half-life? Half-life of a radioactive element is defined as the time interval in which 50% of the radioactive nucleus disintegrates. So the time interval in which half of the nucleus disintegrates or decays is called the half-life. When half-life is reached, then the number of active nucleus becomes n naught by 2, where n naught is the initial number of active nucleus. So now we know that n is equal to n naught e power minus lambda t. Now just replace n with n naught by 2, you will get n naught by 2, n naught by 2 cancelled, take log both sides or take ln both sides, you will get ln2 is equal to lambda t half, or t half is equal to ln2 by lambda. So t half is equal to ln2 is 0.693 divided by lambda. So if you plot the graph between T half and lambda, you will get a rectangular hyperbola because the product of T half and lambda is a constant, right? Now this half-life is independent of the number of nucleus. From here you can see that the half-life is independent of the number of nucleus and it depends only on the decay constant. And decay constant is a property of the nucleus or the type of nucleus. So for a given nucleus, the time period required to become half is same whatever be the initial number of nucleus. For example, initially you have 1000 nucleus. Okay, initially you have 1000 nucleus. Now 1000 to 500, suppose t time is required, then 500 to 250, again t time will be required, then 250 to 125, again t time will be required. So you will see that every time to become half the time required is same. Okay, but the change is different every time. See, here the change is 500, here the change is 250, here the change is 125. Why the time required is same? Because you know that as the number of nucleus keeps on decaying, the rate of decay also keeps on decreasing. So here the rate of decay is more, here the rate of decay is less. That is why the change is less, here the change is more in the same time. Okay, but yes, the time required for the nucleus to become half of its original value or of its initial value is always same. So 10,000 to 5,000 or 5,000 to 2,500 will take the same time. Okay, now what is the physical significance of half-life? So if half-life of a radioactive nucleus is more, that means what? It takes more time to disintegrate. So if half-life of the radioactive nucleus is more, then in a given time, probability of its availability is more because it is having less chance of decay. The half-life of an element does not depend on the physical and the chemical circumstances. It depends only on lambda. And you know that lambda or the decay constant depends only on the type of nucleus and is independent of all other external factors. Okay. Now, suppose at t equal to 0, the number of nucleus is n naught. So at t equal to 0, number of nucleus is n naught. Then after one half-life, it will become n naught by 2. After two half-life, it will become half of this, that is n naught by 2, that is n naught by 2 square. Then after the next half-life, it will become n naught by 2 cube, right? So this will continue. So you will say after one half-life, the number of nucleus becomes n naught by 2. After two half-life, the number of nucleus becomes n naught by 2 square. After three half-life, the number of nucleus becomes n naught by 2 cube. After n half-lives, the number of nucleus becomes n naught by 2 power n. So this n, listen carefully, we have written integer values here, but this n is not necessarily an integer. Okay, n can be any value. So you can write 1.5 t half, you can write 2 t half, you can write 3 t half. So the time is actually n times t half. This n can be 0 0.1, 0 0.2, 1, 2, 3, 4, root 2, 1.2, anything. This n is not necessarily an integer. So n is what? T by t half. Okay, so given time is number of half-lives multiplied by t half. So n is t by t half. So from this you can get n is equal to n naught 2 power minus n, and n can be written as t by t half. So now we have one more way of expressing the number of active nucleus at any time t. The number of active nucleus at any time t is n naught e power minus lambda t, but this can also be written as n naught 2 power minus t by t half. So this is in terms of the decay constant, and this is in terms of t half. Okay, so again I'll repeat, the number of nucleus remaining active after time t can be written in two ways. One is in the form of e power and the other is in the form of 2 power. So in the form of e power you will write n naught e power minus lambda t, and in the form of 2 power you will write n naught 2 power minus t by t half. So after every half-life, again after every half-life, the number of nucleus becomes half of the original value. Okay, so after one half-life it will become n naught by 2, after two half-life it will become n naught by 2 square, after n half-life it will become n naught by 2 power n, but again n is not necessarily an integer. Okay, now the next definition is average life or mean life. So average life or mean life is total life of all the nucleus divided by the total number of nucleus. Okay, or you can say the average of lives of all the nucleus. Suppose the first nucleus survives for 1 second, the second survives for 2 seconds, the third survives for 3 seconds, and infinitely it will go on. Okay, then you will write the life of all the nucleus, the time of life of all the nucleus divided by the total number of nucleus. This is the average life. So the time for which a radioactive material remains active is defined as the mean life of that material. That means the average life or the mean life, tau, is the sum of lives of all the nucleus divided by total number of nucleus. Now, how to find the sum of life of all the nucleus? So the sum of life, you have to take the average of time, right? So the average of time, because there are infinite number of nucleus, so we will not write t1 plus t2 plus t3 plus t4, you will actually integrate over dn. Okay, so the sum of lives of all the nucleus will be integration t dn from 0 to infinity divided by n naught. Okay, now what you will do here, you know that dn by dt is equal to minus lambda n. So dn is equal to minus lambda. N can be written as n naught e power minus lambda t, because we have already calculated what is lambda, what is n in terms of time. Okay, dt. Just replace this dn here and integrate it by parts. You will get the answer as average life is equal to 1 by lambda. I'm not showing you the integration, but you can do it integration by parts yourself, and you will get the mean life tau is equal to 1 by lambda. So from here we can clearly see that the mean life is greater than the half-life. The mean life is greater than the half-life. The average life taken in decaying by the nuclei of an element is defined as its mean life. Okay. Now half-life, mean life and decay constant for a particular nuclei always remain constant, because these are independent of external factors. It depends only on the type of nucleus. Nucleus fixed, that means half-life fixed, mean life fixed, and the decay constant is also fixed. Okay. So half-life is less than the mean life. This is very important because half-life is 0.693 by lambda and the mean life is 1 by lambda. So the mean life is more than the half-life. Okay. Now next is ln n by n naught is equal to minus lambda t. Okay. Because when you integrate this, dn by n is equal to minus lambda dt, you will get this. Ln n by n naught is equal to minus lambda t. So sometimes what they can ask you, the graph between ln n by n naught and t. So if they ask you the graph between ln n by n naught and t, you will say that the slope, the negative of the slope is equal to 1 by lambda. Okay, so the magnitude of the inverse of the slope of ln n by n naught and t is known as the mean life. So mean life can also be defined as the inverse of the slope of ln n by n naught versus t graph, the magnitude. Okay, because the slope will be negative. Now next is very important. If t is equal to 1 by lambda, you know that n is equal to n naught e power minus lambda t. Now if you put t is equal to 1 by lambda, in that case you will write n is equal to n naught e power minus lambda into 1 by lambda. Lambda lambda getting cancelled and you will say n is equal to n naught e power minus 1, and that is n naught by e. Now we also know that 1 by e is 0.37 and 1 minus 1 by e is 0.63. Okay, so that means after one mean life, the number of active nucleus becomes 37% or 0.37 times the original number of nucleus. Okay, mean life of a radioactive nuclei is equal to that time in which the number of active nuclei left becomes 1 by E or 0.37 times the original nuclei, or approximately 37% of the original nuclei. So mean life is also defined as the time in which the number of active nucleus is 1 by E times the original nuclei, or the original number of nuclei, or approximately 37% of the original number of nuclei. Similarly, the number of decayed nuclei will become n naught minus n, that is n naught minus n is what? N naught by E. So from this you will get n naught into 1 minus 1 by E, that is 63% of n naught. So mean life is also defined as it is equal to that time in which the number of decayed nuclei becomes 63% or 0.63 times or E minus 1 by E times the original nuclei. Okay, now we will discuss the graph between the number of active nucleus versus time. Now we know that the number of active nucleus after any time t is equal to n naught e power minus lambda t. So this is an exponentially decreasing function. That means the number of active nucleus decreases exponentially with time. Okay, now we know that the number of active nucleus becomes n naught by 2 at a time equal to t half, and at the average life, suppose this is the average life or the mean life represented by tau, the number of active nucleus becomes n naught by e, or you can say 0.37 times n naught. So at half life the number of active nucleus becomes n naught by 2, and at mean life the number of active nucleus becomes 0.37 n naught. Okay, and from this you can clearly see that the slope of this graph represents what? The slope represents the rate of decay, right? So the slope of graph represents rate of decay. So slope of graph represents rate of decay, and from this we can clearly see that the slope decreases. The slope keeps on decreasing. Okay, now if the slope keeps on decreasing, that means the rate of decay keeps on decreasing, and we know that as the number of nucleus decreases, you will say that the rate of decay also decreases. And this graph also shows that, because as the time passes the number of active nucleus decreases, and the number of active nucleus decreases means rate of decay decreases. So here the slope is decreasing. Okay, so the slope of graph represents rate of decay and it decreases with time. Okay, now if you draw the graph between the number of decayed nucleus and time, now you know that the number of decayed nucleus is increasing, right? Because initially the number of decayed nucleus was 0, and now the number of decayed nucleus is n naught into 1 minus e power minus lambda t. So at t equal to 0, the number of decayed nucleus n dash is 0, and at t equal to any time t, the number of decayed nucleus becomes n naught into 1 minus e power minus lambda t. Okay, so it will start from 0, and at t equal to infinity it will reach up to n naught. Okay, now if you plot these two simultaneously, the number of active nucleus and the number of decayed nucleus, what will you see? You will see that at t equal to t half both becomes equal, obviously, because both becomes n naught by 2. Right, so the active nucleus constantly decreases and the decayed nucleus constantly increases. Right, now let us complete this table. See, at t equal to 0, let us say that the number of active nucleus was n naught and the number of decayed nucleus was 0. So now the decay has just started. At t equal to 1 t half, the number of active nucleus becomes n naught by 2, and the number of decayed nucleus becomes n naught by 2. the ratio of active to decayed nucleus becomes 1:1. So whenever you see that the ratio of active to decayed nucleus has become 1:1, that means half or one half-life has elapsed. Okay, then the percentage of the nucleus that still remains active is 50%, and the percentage of nucleus that has decayed is again 50%. Okay, then what happens at 2t half? So at 2t half you will say that the number of active nucleus becomes n naught by 4 and the number of decayed nucleus becomes 3 n naught by 4. So the ratio of active to decayed nucleus becomes 1:3. So whenever you see that the ratio of active to decayed nucleus is 1:3, you will say that 2 half-life has elapsed. Okay, so this will be 25%. So the number of active nucleus now left after 2 half-life is 25%, and the number of nucleus that has decayed becomes 75%. Sometimes they can also ask you in the fraction form. Okay, so you will say 25% means 1/4 and 75% means 3/4. Okay, then what happens after 3 half-life? After 3 half-life you will say that it becomes n naught by 2 cube, that means n naught by 8. This becomes 7 n naught by 8. N naught minus n naught by 8 is 7 n naught by 8. So after 3 half-life the number of active nucleus becomes n naught by 8 and the number of decayed nucleus becomes 7 n naught by 8. Okay, and this ratio becomes 1:7. So the ratio of active to decayed nucleus, if you see in the question that the ratio of active to decayed nucleus is 1:7, it should strike your mind immediately that 3 half-lives have elapsed or passed. Okay, then the percentage of active nucleus here will be 12.5% and the percentage that has decayed is 87.5%. Okay, then 4 half-life. What happens after 4 half-life? After 4 half-life this becomes n naught by 16. Okay, so after 4 half-life it becomes, the number of active nucleus becomes n naught by 16 and the number of decayed nucleus then will become 15 n naught by 16 and the ratio of active to decayed nucleus becomes 1:15. As soon as you see 1:15 in the question, what should immediately strike your mind is that 4 half-life has passed or elapsed. Okay, if you want to write it in percentage terms, this will be 6.25%. So after 4 half-life, 6.25% of the nucleus remains active and the remaining 93.75% of the nucleus has decayed. Okay, then what happens after n half-life? After n half-life, the number of active nucleus is n naught by 2 power n and this becomes, number of decayed nucleus is n naught minus n naught by 2 power n. Okay, now you can take the ratio yourself. Now what happens after one average life? After one average life, the number of active nucleus is n naught by e and the number of decayed nucleus is n naught into 1 minus 1 by e and the ratio becomes 1 by e is to 1 minus 1 by e. Okay, then after life it becomes n naught by e square and this becomes n naught into 1 minus 1 by e square and after nth mean life you will say it becomes n naught by e power n and this will be n naught into 1 minus 1 by e power n. Okay, so sometimes they can also ask you all these in fraction terms also. So I'll write here this becomes 1/8. Okay, 1/8, 1/8. Okay, and this becomes 7/8. Then this become 1/16 and this becomes 15 by 60. Okay, so now this was actually 15th. I have written 5 by mistake. This was 15. Okay, now number of nucleus left after time t is n naught e power minus lambda t. We already know this. The number of nucleus decayed after time t is n naught into 1 minus e power minus lambda t. We know this also. Now, suppose in the question it is given that the ratio of active to decayed nucleus is x. Then you will write the ratio e power minus lambda t divided by 1 minus e power minus lambda t is equal to x. So from this you will get e power minus lambda t is equal to x minus x e power minus lambda t. So from this we will get e power minus lambda t into 1 plus x is equal to x. So from this, when we solve this, we will get t is equal to ln x plus 1 by x divided by lambda. So they give you, if they give you the ratio of the number of active nucleus to the number of decayed nucleus, then we can find the time elapsed. The time elapsed will be ln x plus 1 divided by x divided by lambda. Okay, now using the chart that we have discussed just now and using this property, let us do some simple questions. The first thing is to find the time in which A, the number of nucleus becomes half. Now, number of nucleus becomes half in 1 T half, right? So the answer will be T because the T half is given as T. Okay, the first question answer is very simple and it is T. Then find the time in which the number of decayed nucleus is 3/4 of the original nucleus. Now you know that from the chart 3/4 of the original nucleus means what? Means two half-life has elapsed, right? So two half-life has elapsed, that means the time is 2t. So find the time when the number of decayed nucleus is 7/8 of the original nucleus. That means only 1/8 is left. 7/8 has decayed. 7/8 is decayed after 3 half-life. Find the time after which 15/16 of the original nucleus has decayed or 1/16 of the original nucleus is left. The answer will be 4 half-life. Then percentage wise also they can ask. Find the time when the active nucleus is 6.25% of the original number of nucleus. So if the active nucleus is 6.25%, then the decayed nucleus is 93.75%. Now the decayed nucleus is 93.75% after 4 half-life. So this answer will be 40. Then find the time when the number of active nucleus becomes 3.125%. Now the active nucleus becomes 3.125% after 5 half-lives. So answer will be 5 half-life. Okay. Then find the time when the number of active nucleus becomes 12.5% of the original number of nucleus. So the number of active nucleus becomes 12.5% or the number of decayed nucleus becomes 87.5% after 3 half-life. Okay. Then they can also ask you in terms of ratio because in the chart we have written the ratio also. Find the time when the ratio of active to decayed nucleus is A 1:1. So 1:1 means 1:1 means what? 1 half-life. 1:3 means 2 half-life. 1:7 means 3 half-life. 1:15 means 4 half-life. Okay, so the answer will be T, 2T, 3T, 4T and 1:2. So 1:2 means, so this is not a integral multiple of half-lives, but you know that T is ln x plus 1 by x divided by lambda. So the ratio is x. So in this case, x is equal to half. I'll just put the value of half and I will get ln 3/2 divided by half divided by lambda. So that means at time ln 3 by lambda, the ratio of active to decayed nucleus becomes half. Okay. Now the next question is, a radioactive sample has 6 into 10 raised to the power 18 active nuclei at a certain instant. Then how many of these nuclei will still be active after 2 half-life? You know that the number of nuclei that is active after n half-life is n naught by 2 power n. So after 2 half-life, the number of nucleus that will remain active is n naught by 4. So that will be equal to 6 into 10 raised to power 18 divided by 4. And that will be equal to 1.5 into 10 raised to the power 18. Okay, now in this question, now this is a very important question for NEET as well as JEE mains. Now the number of uranium 238 atoms in an ancient rock equals to the number of lead 206 atoms. So there is an ancient rock and you are checking the sample of this rock at the present time. Now in this question it is given that uranium 238 and the lead 206, they are in equal ratio. Okay, when you check the sample of this rock, you found out that the concentration or the number of uranium nucleus is equal to the number of lead nucleus. Okay, now the half-life of the decay of uranium is approximately 4.5 into 10 raised to power 9 years. So the uranium 238 half-life is given to you as 4.5 into 10 raised to power 9 years. Then estimate the age of the rock, assuming that all the lead has come from the decay of uranium 238. That means what they're asking you is, you have to assume that at t equal to 0, there was only uranium. That t equal to 0 means the rock was formed. At t equal to 0 means the rock was formed. So uranium 238 was suppose N naught, and lead 206 was 0. There was no lead. Now at the present time, uranium is to lead is 1:1. Now uranium is the active nucleus and lead is the decayed nucleus. If they are in the ratio of 1:1, then you will say that one half-life has elapsed, right? So if one half-life has elapsed, that means what? That means the age of the rock is equal to the half-life of uranium, because at the present time one half-life has elapsed. So you will say that the age of the rock is 4.5 into 10 raised to power 9 years. Therefore, age of rock is 4.5 into 10 raised to the power 9 years. Now in the same question, if the ratio was found out as 1:3. Now if the ratio is found out as 1:3, then you will say 2 half-life has passed. Then the answer will be 9 into 10 raised to power 9. If they ask you that the ratio of the uranium to lead atom is 1:7, in that case you will say 3 half-life has passed. So 3 half-life means 3 into 4.5 into 10 raised to power 9 years. So if they say that the ratio is 1:15, in that case you will say that 4 half-life has passed. That means the answer will be 4 into 4.5 into 10 raised to power 9 years. Okay. Now if they say the ratio is 1:4 of the uranium to lead, then what is the age of the rock? So in this case, if you remember, we have discussed the time elapsed for a given ratio is ln x plus 1 by x divided by lambda, right? And this can be written as ln x is 1 by 4. So you will write ln 5 by 4 divided by 1 by 4 divided by lambda. So the time elapsed will come out to be ln 5 by lambda. Okay, so the time when the ratio becomes 1:4 is ln 5 by lambda. Okay, now they have given you t half, they have not given you lambda, but from t half is equal to ln 2 by lambda, you will say lambda is equal to ln 2 by t half, right? So you'll just put the value here and you will say ln 5 divided by ln 2 divided by t half. So this is the age of the rock when the ratio of uranium to lead sample is 1:4. Okay, so for any ratio you can now find the age of the rock. This is a very important question. Again, I am telling you, you should know how to solve these problems. The next thing that we are going to discuss is activity. Activity is represented by either A or R. Okay, now we will represent it with A, but you can represent it with R also. Okay, now activity is defined as the rate of radioactive decay of nuclei. So activity is defined as the rate of radioactive decay of a nuclei. It is denoted by either A or R, I have told you. So the activity is nothing but the rate of decay. Now we know that the rate of decay, the magnitude of the rate of decay is lambda into n. So the activity is equal to lambda into n. Okay. Now A is also equal to minus dn by dt, because activity is the magnitudes. Okay. So dn by dt is negative. So minus and minus will become positive. So A is equal to minus dn by dt, and you know that n is equal to n naught e power minus lambda t. So activity is lambda n, and n can be written as n naught e power minus lambda t. Lambda into n naught, this lambda into n naught is called initial activity and it will be represented by A naught. So this is initial activity. Lambda into n naught is the initial activity and it will be represented with A naught. So you will get A is equal to A naught e power minus lambda t. So the activity also decreases exponentially with time, just like the number of nucleus. In fact, it is the relation is same, okay, only instead of n naught we are writing A naught, right? So activity is the rate of decay. So the unit of activity will be disintegration per second or decay per second. Okay. So SI unit of activity is called becquerel. 1 becquerel means 1 disintegration per second. That means in 1 second, 1 nucleus is getting decayed. Then the activity is called 1 DPS or 1 becquerel. But 1 becquerel is a very small unit of activity. A larger unit is 1 curie. 1 curie is 3.7 into 10 raised to power 10 becquerel or 3.7 into 10 raised to power 10 DPS or disintegration per second or decay per second. Now, what is 1 curie? 1 curie is the activity of 1 gram of radium. Okay, this mass is important because as the number of nucleus decreases, the activity also decreases. Why? Because activity is directly proportional to the number of nucleus. So if it is said that it is the activity of 1 gram radium, that means the mass is fixed 1 gram. The mass cannot be less or more. Okay, activity of 1 gram of radium is 1 curie. Okay, so 1 curie is defined as the activity of 1 gram of radium nucleus. All right, then there is one more unit of activity and that is 1 Rutherford. 1 Rutherford is 10 raised to power 7 becquerel or 10 raised to power 7 disintegration per second. Okay, now just like number of nucleus decreases to half after 1 half life and after n half life it becomes n naught by 2 power n. Similarly, activity after n half life will be a naught by 2 power n, that is a naught 2 power minus t by t half. So activity after n half life is equal to a naught by 2 power n. That means after 2 half life the activity will be a naught by 4 or the fraction will be 1 by 4. Okay. After 3 half life, the activity will be a naught by 8 or the fraction will be 1 by 8. Okay. Then suppose you have small m gram of any nucleus. Okay. So you have small m gram of any radioactive nucleus. Now the molar mass is suppose capital M. Then molar mass of nucleus, if you have molar mass of the nucleus, then you have Avogadro number of nucleus, right? So unit mass will have Na by m number of nucleus. So if you have small m gram of a substance, then the number of nucleus will be Na by capital M into small m. So the number of nucleus for a given mass of a substance is equal to the Avogadro number divided by m. M is the molar mass and this is the given mass. So capital M is the molar mass and this is the given mass. Okay. So for a given mass of a substance, the number of nucleus is Avogadro number divided by molar mass multiplied by given mass. Okay. Now listen carefully. N is equal to n naught e power minus lambda t. Now number of nucleus can be written as Na by m into small m. N naught can be written as Na by m capital M into m naught, where m naught is the initial mass of substance and small m is the mass of the substance at any time t. Okay, so from this you will get m is equal to m naught e power minus lambda t. So the mass of the radioactive substance decreases with time according to this relation. So the mass of the substance decreases with time exponentially. So mass of substance also decreases with time exponentially. The mass of substance also decrease with time exponentially. Okay. Now in this question they have given you the decay constant for the radioactive nuclei Cu64 is 1.6 in 1.516 into 10 raised to power minus 5 per second. So they have given you the value of lambda. Lambda is 1.516 into 10 raised to power minus 5 per second. Then find the activity of the sample which contains 1 microgram of this. The atomic weight of copper is given to you is 63.5 gram per mole. Okay, neglect the mass difference between the given radioisotope and the normal copper. So we'll have to take the molar mass of the isotope also as 63.5 gram per mole. Okay, so now 63.5 gram means Avogadro number, right? So 63.5 gram means Avogadro number. 1 gram means Na by Avogadro, means Avogadro number by 63.5 gram. Okay, then given mass is how much? 1 microgram. So 1 microgram contains how much nucleus? Na by 63.5 multiplied by 1 into 10 raised to power minus 6. So this is the number of nucleus. This is the number of nucleus that is given to you. So the number of nucleus when you calculate will come out to be 9.45 into 10 raised to power 15. Okay. Now once you have the number of nucleus, then activity is what? Activity is equal to lambda into n. Now once you have the value of n, you can calculate the value of activity. So the value of activity will be lambda multiplied by n, and that will be equal to 1.43 into 10 raised to power 11 disintegration per second, and that is equal to 3.86 curie. Okay, so the activity of copper 64 is 3.86 curie for 1 microgram of the sample. Okay, the mass is important. As the mass change or as the number of nucleus change, the activity change. Activity keeps on changing. Activity decreases with time because the mass constantly decreases, because the number of nucleus constantly decreases. Okay. Now the next question is, the half-life of a radioactive nuclide is 20 hours. So they have given you the half-life is 20 hours. Then what fraction of the original activity will remain after 40 hours? 40 hours means 2 half-life. So after 2 half-life, how much activity will remain? A naught by 2 square, that is A naught by 4. That means 1/4 of the activity will remain after 2 half-life. 1/4 of the activity will remain after 2 half-life. Okay. Now the next question is, the half-life of gold 198 is 2.7 days. That means this gold unstable nucleus is decaying to half in 2.7 days. Then calculate the decay constant. So this is very simple, right? T half is ln2 by lambda. Okay, now what they have given you? They have given you half-life. They have given you this, you have to calculate this. So lambda will be equal to 0.693 divided by T half, and that will be equal to 2.9 into 10 raised to power minus 6 per second. What we have done here is we have written days into seconds. Okay, one day is how much? 86400 seconds. So you have to just multiply with 86400. This is 86400. Okay, then the next thing is, what is the average life? Now average life is 1 by lambda. Once you have calculated the value of lambda, you can calculate 1 by lambda. 1 by lambda will be 1 by 2.9 into 10 to the power minus 6 second, and that will be equal to 3.9 days. Okay, then the next is what is the activity of 1 milligram of gold? So the activity of 1 milligram of gold 198 will be, so first you have to find the number of nucleus, right? Because we have already calculated the lambda. If you get the number of nucleus, then activity is nothing but lambda multiplied by number of nucleus. Okay, decay constant multiplied by the number of nucleus. So number of nucleus, how will you find? You can find it using unitary method. If 198 gram has Avogadro number of nucleus, then 1 gram will have Avogadro divided by 198. Then 1 milligram will have Avogadro divided by 198 into 1 milligram. So from this we will get the number of nucleus. So the number of nucleus will be Avogadro number into 1 milligram divided by 198 gram. And from this we will get the number of nucleus is 3.03 into 10 raised to power 18. Now once you get the number of nucleus, you get the activity by multiplying it with lambda. Okay, you will get 8.8 into 10 raised to power 12 disintegration per second, that is equal to 240 curie. So the activity of 1 milligram of gold is 240 curie. Okay. Now, what is the fraction of active nuclei left after time t? So the fraction of active nuclei left after time t is equal to n by n naught. And the fraction of nuclei left after time t is also called the probability of survival. That means the probability that a nucleus survives after time t is equal to n by n naught. But you know that n is n naught e power minus lambda t, right? N is n naught e power minus lambda t. So you will write the probability that a nucleus survives after half after time t is e power minus lambda t. Now they can give you any value of time. You'll have to put it here and you'll get the answer. But you know also that e power minus lambda t can be written as 2 power minus t by t half. We have seen that before. Okay, so they can ask you in terms of e power something or 2 power something. Okay, you can answer in both ways. Now, the probability that a nucleus survives after n half-life. So just replace this t with n t half. T half will cancel and the answer will come out to be 2 power minus n. Then find the probability that a nucleus survives after n average life. So if they are giving you an average life, then average life is 1 by lambda, right? So just replace here with n by lambda. You will get e power minus n. So the probability that a nucleus survives after n average life is e power minus n. So they can give you 1 average life, 2 average life, 3 average life. Okay. Then the probability that a nucleus decays after time t. Now this 3 was nucleus is surviving. Now they are asking the probability that the nucleus decays after time t. So when they ask you the probability that the nucleus decays after time t, you will just write 1 minus e power minus lambda t or 1 minus 2 power minus t by t half. If they tell you probability that a nucleus decays after n half life, you will write 1 minus 2 power minus n. If they ask you what is the probability that a nucleus decays after an average life, you will write 1 minus e power minus n. Okay. Now, when the decay process is too slow, in that case, n is equal to n naught e power minus lambda t can be replaced as n is equal to n naught 1 minus lambda t. What we have done here is e power minus x is nearly equal to 1 minus x. This is the expansion of e power minus x when x is very small. Okay, so here if lambda t is very small, then you can write e power minus lambda t is nearly equal to 1 minus lambda t if lambda t is very small. Okay, so in that case what we will do is n can be written as n naught 1 minus lambda t and n is equal to minus n naught lambda t plus n naught. So on comparing it with y equal to mx plus c, this is y equal to mx plus c, you will get this is a straight line with a negative slope minus n naught lambda and the positive y-intercept which is equal to n naught. Okay, now this is a very important question. Everybody listen to it very carefully. Suppose the daughter nucleus in a nuclear decay is itself radioactive. What they are saying is there is a daughter nucleus, but this nucleus is also radioactive. Now, if this nucleus is also radioactive, in that case, it might decay to a new nucleus that is C. Okay. Now, let lambda p be the decay constant of the parent nucleus and lambda d be the decay constant of the daughter nucleus. Also, let np be the number of parent nucleus at any time t and nd be the number of daughter nucleus at that time t. Then find the condition for which the number of daughter nucleus becomes constant. That means nd does not change. Okay. Now, the rate of decay of B dNB by dt is equal to, now you have to listen carefully because here B is not only getting decayed but also it is formed, right? So the rate of formation of B will be lambda P into NP because the rate of formation of B will be the rate of decay of A. Now A is decaying at a rate lambda P NP. So B is forming at the same rate that is lambda P NP. Now, but this B is also decaying, right? So if this B is also decaying, the rate of decay of B is lambda D into NB. So I'll write minus. Now I have to write minus because now it is decaying. Here it was forming, so NB was increasing. Here NB is decreasing, so the rate has to be negative. Okay, so I'll write lambda D into NB. Now, what they are saying is find the condition such that the number of daughter nucleus becomes constant. That means dNB by dt becomes 0. Okay, so I'll write it as 0. Then I will get lambda p np is equal to lambda d nb or nd. So this is the condition that the number of daughter nucleus remains constant The condition is lambda p and p is equal to lambda d and d. But this is the more important thing here, that you have to understand how to write the rate of decay of B, because B is not only getting decayed but it is also getting formed. Now when you see the rate at which it is formed, you will not write lambda p into nd, but you will write lambda p into np, because the rate at which A is decaying is the rate of formation of B. Rate at which A decays is equal to the rate at which B forms. Okay, because B is formed from the decay of A only. Okay, so when you write the rate of formation of B, you need the number of nucleus of A. But when you write the decay of B, you need the number of nucleus of B. Okay. Now, in this question, it is given that a radioactive sample decays with an average life of 20 millisecond. So that means they have given you the value of average life, T average is 20 millisecond. That means the value of lambda is 1 by T average, because T average is 1 by lambda. So lambda is 1 by T average, that is 1 by 20 per millisecond. So they've given you the value of lambda or the decay constant. Now we have a capacitor of capacitance 100 microfarad and it is charged to some potential. So we have a capacitor whose capacitance is 100 microfarad and it is charged to some potential and it is connected through a resistance R. So now it is becoming a decay circuit of the capacitor, the RC decay circuit. Okay. Then what should be the value of R so that the ratio of the charge on the capacitor to the activity of the radioactive sample remains constant. Now we know that the activity at any time t is given by A is equal to A naught e power minus lambda t. Okay, where A naught is the initial activity at t equal to 0. Okay, and similarly the charge on the capacitor as a function of time is given by Q is equal to Q naught e power minus t by RC. So if you divide A and Q, they are saying that the ratio should be independent of time. Okay, so ratio should be independent of time. In that case, Q by A is equal to Q naught by A naught e power minus t by RC divided by e power minus lambda t. Okay, now it is independent of t if lambda becomes equal to 1 by RC, because if lambda becomes equal to 1 by RC, in that case this two will get cancelled out. So if lambda is 1 by RC, now lambda is given to you as 1 by 20 millisecond per millisecond. Okay, just you put this value and you will get the value of resistance. Okay, now we will discuss parallel or simultaneous decay. Now what is parallel or simultaneous decay? Sometimes a radioactive nucleus decays into some other nucleus using one or more path. Okay, so what happens is this radioactive nucleus is decaying into B, and when it decays into B, the rate constant is lambda 1. When it decays into C, its rate constant is lambda 2. But what happens sometimes is it decays into B and C simultaneously. This type of reaction or this type of nuclear reaction is called a parallel reaction. Okay, it decays into lambda 1 and lambda 2 simultaneously. Okay, in that case you will say that dNA by dt, that is the rate of decay of A, is equal to minus, because it decays using this and this path simultaneously, so you will say that the equivalent decay constant is lambda 1 plus lambda 2 into Na. So the rate of decay of A is equal to minus lambda 1 plus lambda 2 into Na. Okay, so the lambda equivalent will come out to be lambda 1 plus lambda 2. So when you solve this, you are going to get Na is equal to N naught e power minus lambda 1 plus lambda 2 into T. Okay, now again lambda equivalent is equal to lambda 1 plus lambda 2. Right? Now what they have given you in the question, the half-life when this is occurring is T1. The half-life when this is occurring is T2. Okay, in that case what they are asking is what is the half-life when both are occurring simultaneously. So when both are occurring simultaneously, then lambda becomes lambda equivalent. Okay. Now we know that T half is ln2 by lambda. So lambda can be written as ln2 by T half. Okay. So lambda equivalent can be written as ln2 by T half equivalent. Now T half equivalent according to this question is T. Similarly, lambda 1 is ln2 by T1 and lambda 2 is ln2 by T2. Okay, ln2 getting cancelled. So you will get 1 by T is equal to 1 by T1 plus 1 by T2. You will have to remember this. This is the formula for equivalent T half. This is the formula for equivalent T half and you have to remember this. This is the equivalent T half. Okay, so from this you can see that the equivalent T half is smaller than individual T half. Why? Because see, if only this path was happening, suppose the half-life is 20 days. If only this path is happening, suppose the half-life is 40 days. Then when both are happening simultaneously, then obviously it will decay more fast. If it decays more fast, then the half-life will decrease. Okay, so that is why when two or more reactions will occur simultaneously, in that case the half-life will be smaller than the individual half-lives. Okay, now the same relation can be asked for average life also. So if T is representing the average life instead of half-life, then for average life, from here instead of lambda equivalent I will write now 1 by T. Okay, why? Because now T is not the half-life but the average life. Okay, so I will write lambda equivalent is 1 by T, lambda 1 is 1 by T1 and lambda 2 is 1 by T2. Still you will get the same relation. So for average life also you will say 1 by T is equal to 1 by T1 plus 1 by T2. So that means this is the average life, the equivalent average life. This is the average life of first reaction and this is the average life of the second reaction. So average life will also decrease. With this we come to the end of today's lecture. In the next class we will be discussing about the sequential decay. Today we have discussed about parallel decay. In the next class we will be discussing about sequential decay and we will also discuss the nuclear fission and fusion elaborately. Okay, so till then stay tuned and see you guys again in my next lecture. If you like my video, do hit the like button and share my work with your friends, your juniors, your seniors and any other student who is preparing for JEE, NEET and any other competitive exam. Also, subscribe to my channel and hit the bell icon so that you get notified whenever I upload my next video.